Okay, I think I'm live. Stream health. Let's see. Yeah, I think I'm good. Okay. Okay, cool. We are live. So, where do I even start? Okay, so I am currently in the process of trying to complete the Leetcode 150. And if we look at the roadmap, I have about 126 that I've done. I know like 90% of them. But as you can see from my Leetcode heat map, I was doing really well for about 61 days, and then I just recently broke my streak, which was quite heartbreaking. So, to keep myself accountable, I have decided to document all of this and see where this goes. So yeah, I'm getting a YouTube error right now though. Let me see. How do I change? Okay, what is this error? Oh my gosh. Oh, okay. I have to change my latency. Huh. Can't change it during stream. Whatever. Okay, cool. Yeah, so again, just wanting to document this, and we'll see where it goes. So, so my plan right now is, as you can see, I haven't done anything in the past few days, or a couple days, and I've been really bad with it. So, currently, have about 90% of the 150 down, or sorry, 90% of the 126 that I've solved down. But I haven't really made an emphasis on, understanding time complexity to its fullest extent, and then also understanding, there's some problems where like I know the answer, but I know the answer, but I don't know exactly why it works. So I am treating however long it takes to brush up on my understanding of all this, and then I'm going to start working on the newer problems and learning the newer techniques and fundamentals. Let's see. Yeah, so I have this set up. This is going to be my notepad for the stream. So yeah, going to go through all of them right now just to see what I know and what I remember and then what I don't remember. And then I'm going to write down all the problems that I don't necessarily know the time complexity to, and the problems that I don't necessarily know the solution to. So yeah, let's go. Let's start. Let me get this started. Okay. So it's here. We have to make a set. I also need to practice like thinking out loud, and I don't do that normally, so I think this is a good opportunity to do that. Okay, so we have to create a set with integers, and then for each number in the array, we're going to see if we can add set or add a number in the set. And then if we can't, we're going to return false. And then we'll return true when we go through all the conditions. Oh, is it the other way around? Oh yeah, contains duplicate. Whoops. What the heck? Okay. Cool. Yeah. Yeah, and these first, I mean, I'm pretty good at most of them, but these first, like the hashing and the arrays are pretty easy. Cool, so here we have to make frequency lists, but if we can check the length of both of the strings, and if they don't equal each other, we can just return false. And then, yeah, we have to create a frequency array, 26 characters, because that's how many letters there are in the alphabet. And then a loop through each character. And we'll increment every time we encounter a character in the S string, and then we'll decrement or decrement every time we see something in the T string. Oh, T string. Oh, that's why. Is that really it? Oh, that's why I keep on messing it up. I might have to change my keyboards. Okay. Oh, and then, so then we'll loop through. Oh, I forgot to mention the time complexity of the other one. We loop through the frequency array, and if anything in the frequency array does not equal 0, we're going to return false. Otherwise, we're going to return true. Okay. Cool. Yeah, okay, so this is O of n, time complexity, and then O of n space complexity as well. Yeah, and then contains duplicate is O of n, time and space as well, I believe. Do some, yeah. So here we're basically, we're just making a hash map where we store previously iterated values. So we'll iterate through each value. We'll find the complement of each, which is just the target subtracted by the current number. And then if the hash map contains the key of the complement, we're going to return a new array with its index, the complement's index, and it's the current index. And then we'll take the map, and then we'll put, after each iteration, we'll just put the currently iterated value into the map. And then this will just be an exit condition, because this will always return a, oh my gosh, I keep on hitting the wrong keybind. Okay, this will always return a value. We'll never reach line 15, basically. Okay, this occurs in O of n time, O of n space as well. Yeah, cool. Okay, group anagrams. How do we do this? Okay, so we're going to create the output structure and then iterate through each string. Iterate through each string. And then we're going to create a frequency array. Same thing we did last time for anagrams. And then I need to change the title of the stream actually. Wait. Leetcode. What do I name it? Leetcode. Practice. Oh, actually, I'll name it Leetcode 150 day 1. How do I change the category? Education. Science and technology education. Maybe I'll just leave it as people. Yeah, we'll do that. Okay. So we iterate through all the strings, we create a frequency array, and then and then we do. Okay, so we're supposed to make a key for each word, basically. So we iterate through the word, and then we find the character, each character, and then iterate it. And then we can make a key, basically, out of that frequency array. So yeah. And then we use this key from the frequency array to put it in, to group the anagrams, basically. But I need, oh my gosh, I keep on doing that. Okay. I need a hash map to store the key and the list of words in each key. Yeah. So once we're there, we're gonna check if the map contains this key first, and if it doesn't, then we're going to gonna put it in the map. So, and then it's new array list. Yeah. And then we get the list, and we add the current string, and then we're done. So the map will have each anagram and a list of the associated words. And what I think we can do is we can actually move this down here and then just do map.values. Yeah, values, and I think we can just return this value if I'm not mistaken. I think that'll work. Oh, whoops. Yeah, perfect. So this happens in space complexity of O of n for sure, and then this is O of n here, and n will be the size of, or the number of words. So space complexity is definitely O of n. Time complexity, this is O of n. Okay, so it's, I think time complexity will be O of n times m, where n is the number of words and m is the average length of each word. Yeah, let's ask GPT actually. Okay, so what is the time and space complexity of this? Yeah, yep. Oh yeah, I forgot. This happens in O of n as well, but that shouldn't matter. Oh no, this happens in O of, this is constant because the frequency array is 26. So that's O of 1. Yeah. Time complexity is, space complexity is O of n. Wait, why? Yep. The hash map can have at most n keys. Okay. And the value list. The space complexity for storing all strings in the map is O of n. What is this? Oh, it's the dot. Wait, I don't get it. All strings are unique. The hash map can have at most n keys. I get that. The keys is equal to the length of the word, or the number of words. Can you explain why space complexity includes the length, or the average length for each word? Denoted as m. Mm-hmm. Mm-hmm. String has a fixed length. Yep. Yep. The value associated with each key is a list of strings. Yep. Oh. Do I just have to consider the length of each string? I didn't know that. Oh, okay. So I just have to consider the length of each string. Okay, cool. Cool. Did I submit this here? Okay, cool. That's done. See, that's why I'm doing this, because I need to know that stuff. Okay. Top K frequent elements. What do I have to do here? Oh. Okay, so we're gonna make a hash map that stores, it's a frequency hash map basically. It stores each number and how frequent it occurs. So we'll iterate through the numbers and then we'll put in the map the current number and the previous count of the number plus 1 to iterate it. And then I actually think we need another data structure. So we're gonna need an array of array lists. Freq equals new list like this, and yeah, I think it's that. So then we have to iterate the maps values for every key and value in the map. If the current value's frequency or has nothing in there, so if this equals null, then yeah. Okay, so this problem's dependent on the number. There won't be a number greater than the size of the array, which sucks because like Leetcode should tell you that, but I don't think it does. K is the range 1. Yeah, I don't think that this just tells you that. This just tells you the number of unique elements. Yeah, it doesn't tell you that each number will be between 1 and the size of the array, which is dumb because it's like, if I knew that, I probably could have solved this in the first place, but no. Or I could have solved this like the first time trying. It would have been a lot easier, but they don't tell you that. Okay, and then we add the value. Okay, so we've iterated through the map. We've added this. Okay, so now we have to iterate through the frequency array. Length minus 1, I is greater than 0, I minus 1. Okay. So if the current value is not null, Yeah, I'm gonna have to switch my keyboard. I'll do it after this problem. So if the current frequency has no numbers, then we don't want to touch it. And if it does, then we want to put it in our output array. So we're going to make our output array. And then we also have to track the index of the output array. So then, yeah, and then we have to iterate through. Yeah, so if we have values that have a frequency, if we have values that have a frequency, then we want to add them to the output array. How do we do that? Oh, we iterate through the values in the frequency. That's size. Oh no, not I. It's J. Why did I do that? It's J. Then, yeah, then you go to output index ++ because we want to iterate every time we change the every time we add a value to the output array, we want to change the index or iterate the index. And then it'll be I.get J. And then if the index equals K, then we're going to return the output. And then otherwise, we'll just return the output afterwards. Okay, cool. Do I not have the angle tenor brackets? Is it just this? Object cannot be converted to int. What? Oh, I have to specify the type. Oh, then do I need the angle brackets here? No? Oh, whoa, what happened? It's adding 3 then 2. Is it going the opposite direction? So dumb. It's this. There you go. Oh my gosh. There we go. Okay, time complexity. O of n, where n will be the number of values. This is technically O of n, even though they're 2 loops, because we can guarantee that, because all we're doing is taking this data structure and putting it into a 2-dimensional data structure here, but our output, our maximum, the maximum amount of iterations that we do is going to be the size of the input array. Yeah, I think that's right. Also, did I submit? Cool. Yeah, let's ask GPT just to make sure. Time complexity. Oh yeah, this is called like bucket sort, right? Is it? I could be totally wrong. Yeah, there we go. Okay. Does this bucket work? Okay, cool. All right, I need to change my keyboard and get. Oh, I have water. Oh my god, this thing is so heavy. Keyboard's too big. I don't want to use it. I'll use the other one. I'll use the one on the lamp. Oh wait, this keyboard's also broken. Maybe I'll have to go to the other one. Oh my gosh. Will it work? Will it work? Let's see. Let's see. It will not work. Looks like we're going back to the other one. Oh my gosh. I did that for no reason. Okay. That's fine. Alright, I'm gonna go back. Okay. change this. Okay, I gotta turn that off. Okay, I don't know if I should name this Leetcode. I think I should just name this Leetcode log. No. Should I just name it solving Leetcode problems? Is there an extra space there? Yeah, there is. Okay, cool. Okay. Alright, we're already distracted enough. Yeah, I saw this. Okay, cool. Oh wait, this is not available on. Yeah. It's cool. We can do this. Okay, so what's the trick here? We need to use a string builder. Yeah, string builder, and then for each string in the array or in the list, I'm going to take the string builder and append what? The length of each string, and then append a break, and then appends the actual string. Yeah, and then we're going to turn string builder to toString. So then to decode, we take that string, and then it's like a two-pointer method basically. Yeah, so while I is less than string.length, I is less than string.length, j equals I. Okay, so we need to iterate the first pointer while I is, oh no, so the current character does not equal the break. Yep, like that. And then when it does hit the break, we have our length. J to I, yeah. Because it's exclusive at the end, so we're fine there. And then, what do? We iterate I once because we want it to start at the word. It's currently at the pound sign. And then we need our output list. Oh my gosh, stop. Output list string output equals new list. Yeah, so then we take our output and then add I plus length. Yeah. And then I plus equals to length. So then we restart to the next. Yeah, I think that's it. Oh my gosh, load. There we go. Cool. So this happens. Is O of n, O of n, O of n. This two-pointer. So we just keep. Yeah, this is this doesn't actually contribute to the time complexity. This is what we're doing one by one. So this is O of n, time, O of n space. Space. At least I think. Okay. Product of an array by itself. Let's see. How did I get this wrong? Why is it M? Oh, I see. Oh wait, no, I'm just gonna, why did I do that? I see. So n is the number of strings in S. Oh, it's because strings take up space. I just learned this. Oh my gosh. Okay, now I know. This actually makes sense. But what's the auxiliary space? Is it any different? Or no, is the auxiliary space any different? Yeah, I was gonna say. It's no extra space. Okay, that makes sense. Encode makes sense too. Okay. Cool. So for this, product of array by itself, we're gonna have an output array, and then you have to multiply everything, or you have to find all the products of each index and every value to the left of it exclusively, and then do the same for the right exclusively, and then add them together, because we can't divide, right? Yeah, without using the division operation. Okay, so 1I has to be less than nums dot length plus. Oops. No, it's not index. It's I need to fill the output array with ones because it just defaults to 0. And if we multiply them, we're gonna get 0. So then output I times equals output I minus 1 times nums I minus 1. Yeah, that's it. And then I have, for this one, I have to keep a rolling product variable and go backwards. So if I equals nums dot length minus 1 is bigger than 0, so then it's output I times equals rolling product. This has to be 1, not 0. And then rolling product times equals nums I. This is just so much easier than doing it the other way. Yeah, and then I can return output. Space complexity is going to be O of n because of this, where n is the number of integers in the array. And then time complexity is going to be O of n because we just, yeah. Cool. What are the faster ones? What? Is this not exactly what it did? What the heck is this too? I don't even know what that is. No, whatever, I don't have to worry about that. That is pretty simple. I don't think I need to go to GPT for the time and space. Okay, what's next? Valid Sudoku. This is just Sudoku validation. And you can use hash sets to simplify the checking. Yeah, so yeah, so we're going to iterate through each value in the board. And then here, we're going to have to make the sets, so it's character, right? Yeah. Set x equals new hash set. Okay, so I'm going to do checker x equals. We flip them to get the opposite, or the inverse. If cur x does not equal period, and stop add cur x to false. And we do the same thing for y here. For y. Oh my gosh, why is it doing that? Okay. And then we need to do the subgrids, the 3x3s. So set character subgrid is new hash set. And then let's go back for each row. And then column is the same thing, but with J. If order row call if cur does not equal the period and subgrid can't add that, then we will return false, and then after this we return true. I think that's it. Ugh. Let's see. Yeah, there we go. Oh, this one's cake. So we make a set of integers. So basically, we have to add all the numbers to the set. It's a hash set. None. And then we have to check if the set contains the current number minus 1. Because if it doesn't contain it, then we know we're at the smallest subsequence for that respective sequence. So now what? What's our output value? Okay. So we're going to track the max. Cur equals nums I. Counter equals 0. And then while set contains cur, we're going to iterate cur and then iterate counter. And then max is going to equal the max between max and counter. And return max. Yeah. Yeah, so this is space of O of n, time of, what? That doesn't seem right. Let's try it again. That doesn't seem right. Oh, is there a faster way to do this? Oh, I'll check that. So this is O of n space, O of n time, O of n time. This is also O of n time. This is not O of n. Yeah, because technically with this algorithm, this if statement makes it so that we only iterate through all the values once, for sure. So this whole thing is 2n. And because of that, we can reduce to n. What? Is there a faster way to do this? Sorting. Oh my gosh. Okay, bro. Yeah, I'm not worried about that. Okay. Oh, well, that's done for that. Palindrome. You have to make S lowercase first. And then left. Character, it's is letter or digit, right? If it's not a character, digit, increment, and then we have to do the same thing for the left or the right. Is letter or digit, right, decrement. S.char at left does not equal S.char at right. Return false. Else left plus plus, right minus minus. True. Yeah. Okay, so space complexity is O of 1, time complexity is O of n, because we're closing the window. Yeah. Okay. This one's pretty straightforward too. When numbers length. What's the point of changing it to numbers instead of nums? Right. If target or no, if sum equals target. This is also dumb. They don't want 0 indexed indexes. It's like, you're just making it hard for no reason. But do they even say that? Like, exactly one solution you may know. So when twice returns indices of two numbers. Yeah, given a 1 indexed error. Like, bro, come on. Int left plus 1, right plus 1. Yeah. And then our exit condition. Oh wait, I'm so dumb. If it's less than target, then we need to increase the sum. Otherwise, we need to decrease the sum. Okay, there we go. So this is O of n space, or O of n time, O of 1 space. Okay, that's done. Doing good so far. I forgot that. Actually, I should probably write that down. So for these, for this, actually, wait, yeah. Okay, so how should I do this? Encode, decode, what is it called? Oh my gosh. Encode and decode strings. The issue with this is, remember time complexity of strings. And then there's another one that has that, right? I think it's group anagrams. Well, actually, let's check GPT. Because I asked it, I was like, why? Why is it? What the heck? Wait, what? Where'd it go? Oh, okay. What string? Which one is this? Group anagrams. Cool. Remember time complexity of strings. Yeah. Okay. Cool. Threesome. So we have to get each permutation of the of values. 3 values that equals 0, that sum to 0, but we don't want duplicates either. So to avoid duplicates, we sort the nums array, and then, yeah. We iterate through each number. If we're at the first index or the preceding or succeeding numbers don't equal each other, then we're good. To be honest, yeah, this is one of those problems where I kind of get how it works, but I don't fully understand how it works. So we'll go back through this after. What do we have to do? I think, yeah, we have to get our pointers. It's target equals 0. Wait, no, we're not doing that yet. We are not doing that yet. Are we even doing the pointers yet? No, we're not. What am I doing? 0 minus nums I. That's what it is. And then, this is when we do this. Well, left is less than right. We don't want it to be equal to, yeah. Let's complement nums left plus nums right. If complement equals target, then we take a list, add nums to I, add nums left, add nums right, and then add the list to the output. And then we just need to automatically skip the duplicate numbers. So while left is less than right and nums left equals nums left plus 1, left plus, and then while, same thing for the right side. Minus 1 though. And then we do it one last time. Yeah. If it's less than target, we need to make the number bigger. Otherwise, you need to make the number smaller. I think that's it. Okay. Time and space. This is one where like I'm not exactly sure. So this is n log n. This is n. This is also n. But these two, n squared. Is this n squared? I think it is. Because we have to go through each number and then the window slowly gets smaller, but we can't reduce that to anything. Yeah, I think this is n, this is n, this is whatever. This is a part of this. Yeah, space might be n. What does n represent? N represents the amount of numbers, yeah. The numbers in the list. And okay, I'm gonna say time is n squared, and space is. I think this might make it n squared as well. Yeah, I think they're both n squared, but this one I really could be wrong, bro. Okay, time's right. Okay, let's not auxiliary. What is the non-auxiliary space? Okay, so I was right. Okay. What the heck? Oh. 37 container with most water. Okay, so here, what do we want to do? We need 2 pointers, the left and the right. Oh my gosh. And while the left is less than the right, we're going to calculate the area. Oh my gosh, why do I keep on doing that? I need to change my keyboard after this. Okay, or remap my keyboard. equals math.min of the left height and the right height times right minus left. So right minus left is x. Yeah. And then max equals math.max. Between max and current area. And then we move the smaller height. Yeah. Left is less than height or right. Left plus else right plus or minus. Return max. Beautiful. Let me check my sound. Okay. Cool. Oh, we're good. What are the faster ones? Are they just like one-offs? Yeah. Yeah, it looks like it. Wait, fast forward. Oh, wow. This is still the same time complexity though. Oh yeah, time. What was time of that was O of n, space was O of 1. We didn't use any extra space. Trapping rainwater. Okay. How do we do this? We need the pointers, so the left pointer and the right pointer. And then we need the height. We need to keep track of the max height, so max left equals height left. Max right equals height right. And then we need to keep track of the amount of water that we can store. So while left is less than right, if the height on the left side is less than the height on the right side, and we'll calculate how much. So if the height on the left side is less than the height on the right side, we can guarantee that we're trapping water on the left side. Otherwise, if it's the opposite, we can guarantee that we're trapping water on the right side. So then, what do we want to do? We need to check if the new left pointer has a greater height than our previous left pointer, or the previous max height. And then we take the water and add the difference between we add the difference between the max height on the left and the current height on the left. And then we iterate the left. And then we do the opposite on the right side. Yeah, I think that's it. Beautiful, beautiful, beautiful. Okay, space. O of 1. Time. O of n. Yeah, O of n. We're just adding some logic. Okay, stacks. Let's see. Stacks. Stacks. What, character? Yeah. So we make a stack. And then we iterate through the string. If the stack is empty, if the stack is empty, we're going to add the current letter. There we go. Otherwise, if the stack, the top of the stack equals an opening parenthesis and cur is the corresponding closing, then we're just going to remove it. Oops. And then we need to do this for each of the different types of parentheses. So we're here. Where's my cursor? Okay. With the square brackets here, and then curly brackets here. And then we'll just push. And then we'll return if the stack is empty or not. Okay, time. Oh my gosh. What did I do wrong? Oh my goodness. There we go. Time. Time is O(n). Space is O(n). Beautiful, beautiful, beautiful. Yeah, it's the same thing. Okay. Min stack. Okay. So we just need to track the minimum in the stack. Yeah. When we push onto the stack, if the min stack is empty or the value is less than or equal to the top of the min stack, then we're going to push it onto the min stack. The value, and then we're just going to push the value onto the stack, the regular stack. Pop if this dot stack dot peak. So if the top of the normal stack equals, for some reason too, okay, maybe I'll add that to the list. But if you use equals here, I'm pretty sure it breaks. It's something about like character or something dereferencing or something like that. This dot min stack dot peak, this dot min stack dot pop. So if the values are the same, we'll pop them, and then this will just pop no matter what. Turn this dot stack dot peak. Return this dot min stack dot peak. Yeah, but I'm pretty sure this is going to break because of the equals sign. Like if I submit, yeah, something here. Like if I do, oops. Like, I think this will be fine, unless I'm completely wrong. Yeah, like I don't, okay, that's something we need to figure out. Actually, wait. I'm just gonna copy this. Why does it matter if we use dot equals versus in which function? In pop. In pop. Method of use. Reference inequality. Okay, is it because we're using the wrapper class? I wonder. Pop. Use the equals versus equal pop method. Checks for value equality. Because we're using the wrapper class, it's an object, and the object reference will be different even though they're the same numbers if we use the equal operator. Well, now I know. Okay, so what is this, min stack? Min stack. Remember, what do I need to remember? Wrapper class equality. There we go, that's a good way to put it. Wrapper class equality. Okay. Oh my gosh, I hate this problem. This one's so annoying. Stacks in general are kind of annoying. Oh, I know. So I'm gonna have a stack of integers. And then I'm gonna iterate through each token. And then we're gonna have a switch statement. I do like using switch statements though. Token. Okay, so what are our... Cool. Plus, minus, multiply, divide, and then defaults. Stack dot push integer dot parsent token. Okay. This is subtraction. This is multiplication. This is division. So when we're adding, we can do stack dot push stack dot pop plus stack dot pop. When we're subtracting, we need to, it'll be out of order because of the stack property. So term 2 equals stack dot pop. Term 1 equals stack dot pop. And then stack dot push term 1 minus term 2. Multiplication, we're fine here. Stack dot pop times stack dot pop. And then division, we need to separate the numerator and the denominator. Numerator equals stack dot pop. Stack dot push. Stack dot, oh no. Numerator divided by denominator. Yeah, division is integer division. And it's one stack dot peak. Yeah, I think that's it. Okay. Space is O of n, time is O of n. Yeah. Yeah, I understand this one. Oh, I forgot. 2-pointed threesum. I don't fully understand how threesum works. So, full breakdown. Do not understand. Okay. Uh-oh. Am I done with stack? No, I'm nowhere near close to done. Generate parentheses. You can do this with a stack. To be honest, I don't know how. Maybe I should figure out how, but I do this with backtracking. DFS. Actually, no, it's not DFS. Actually, is it? I don't know. Backtrack is just way easier. And 0. No, wait. And the string 0, 0 output. And return output. So what we need to do here is we have the number of parentheses, and we just have to generate each permutation of it. So we have our permutation here. We have our permutation here. And then we have the number of open parentheses and the number of closed parentheses, and then obviously our output array or list. So if the length of the permutation equals to twice of n, we're going to take the output and add the permutation. There's a quicker way to do that. You can technically optimize with string builder. Maybe I should, yeah, I'll write that down just to see how to do it. But then you backtrack. So if open is less than the number of parentheses that we need, then we can call backtrack and permutation plus an open parenthesis, open plus 1, close, and then output. And then if close is less than the number of open, because we don't want to put in a close, we don't want to put in multiple closed parentheses if we don't have enough open parentheses to match it. So we have to throttle it like that. We backtrack again to n permutation plus closed parentheses open, and then close plus 1, and then the output. And I think that's it. So the two things with, oh my gosh, did I spell it wrong? I spelled this wrong. Permutation. Okay. Oh my gosh. Beautiful. So the two things, well, first of all, spaces of n, it actually might be more because of how because we're just concatenating strings, which isn't efficient at all. Whoa, actually, yeah, space gets destroyed because we're recursively concatenating strings, I think. Yeah, I have no clue how fast this is, to be honest. I mean, it's pretty slow according to this graph. Jeez. What do these people do? Oh, they do the recursive as well. And they do string concatenation. There's no way. There's no way. Yeah, return, honestly, having return here is probably smart. Okay. How is this one so much faster? Oh, they use a set? Oh. That's kind of genius, actually. Wait, does it really speed it up that much? There's no way. Oh my gosh, conversion, that's why. Yeah, I wonder how much faster this is. Oh, that's crazy. See, this person uses string builder. Okay. Yeah. I don't know time complexity of this because it's recursion and I suck at that. Okay, so we're gonna write that down. Generate parentheses. Is that how you spell it? Yeah. Understand time and space complexity and the string builder implementation. Cool. So we got a lot of work on already, and we're not even like halfway through. Okay. At least I know how to do it. Okay, daily temperatures. Stack. This, yeah, stack. Stack, integer, stack, this new stack. Okay, so the trick to this, length. So we have to create a stack, and then if we encounter, or we store values that have not encountered an increasing temperature or a warmer temperature. We store values that haven't encountered a warmer temperature in the stack as we iterate. And then if we encounter it, then we calculate that. And we do that by taking the stack and storing the index in it rather than the value. So if stack is empty, stack.push temperatures I, and then while stack.p, temperatures stack.peak is less than the current temperature. Temperatures I. Then we need our output array. Int output. There's new int temperatures. Oh my gosh. Temperatures I. So while we have a warmer temperature, output stack.peak equals I minus stack.pop. Yeah. Is that it? I actually think I can simplify this a little bit. Technically, if we do this, is empty. Well, the stack isn't empty and that condition is met, then we can just put this here and then stack and then push. Yeah, something like that. I think this works. Oh, never mind. What? Oh, whoops. I just contradicted myself. Here we go. Okay, space O of n, time O of n. Yeah, that's pretty simple. Actually, is time O of n? Yes, because we only iterate through the list twice, no more. Let's make sure though. What's the time and space complexity of this? Auxiliary is still O of n because we had the stack. Time O of n. Yeah, this iterates O of n max. Space O of n. Beautiful. Beautiful. Okay. car fleet. Okay. Oh. Okay. So, what do we do here? Does this even, do I even need a stack for this? Okay. I don't know if I need a stack for this. So we have to track how many cars get, how many fleets there are based off of cars getting bunched up. So we need a hash map to store the position and the total speed it takes to get to the target. So for every value speed, I didn't give this a name. What are we putting in it? We're putting the position and double position, or no, it's target minus position divided by speed. Yeah, so the remaining distance divided by the speed of the car. So in the hash map, we have each position storing the speed, basically the time it takes to get to the target from that position. So now we can track our fleets, and we need to be able to track the last speed. We also need to sort the position array. Sort position. Because we need to iterate it through it from closest to the target to furthest away from the target. I equals position dot, what the? Position dot length minus 1 is greater than or equal to 0. And we decrement. So if the speed it takes for the current position to get to the target is greater than the last speed, we're going to increment the fleet and make the last speed the current speed. And that's it. I think, yeah, we don't even need a stack for this. Should I learn the stack version of this? Might be worthwhile to do so. I'll write that down. Oh my gosh. Okay. That's pretty fast. Okay. Car fleet. What's the name of it? Car fleet. Car fleet. Optional. Maybe worthwhile to learn stack version of solution. I'm sure there's a stack solution. Oh wait, time and space. We forgot about time and space. Time complexity. Time complexity. O of n. O of n. Okay, times O of n. Space is O of n as well. Let's double check with the GPT just to make sure. Oh, we're sorting. Oh, I totally forgot. That's tragic. That's tragic. We have to sort. This is a pretty fun problem. So we have to take advantage, or we have to create a specific data structure called a monotonic stack, where stacks are either strictly increasing or decreasing. So we'll have a stack, we'll have the index, and while the index is less than the length of the array, if the stack is empty, or the largest value, the current largest value in the stack is less than or equal to the current value of the height. We want to push that value into the stack and then increment it. Otherwise, we have reached a monotonic stack, or we have monotonic stack and we've reached a decreasing value. So then we can calculate the height, which is just stack.peak, and then the width, which is, if the stack is empty, it's the value of the index, and if the stack is not empty, then it's, I think it's that. I don't like that. Nice. Height times width. I'm pretty sure it's this. And then while the stack is in, so that calculates our largest rectangle, but at the end of this iteration, we'll always have a value. We'll always have one last monotonic stack, unless we, actually, is that true? Height, width, stack is empty. Yeah, we'll always have one monotonic stack, because once we increment the index and then we add it, we'll be out of bounds. So while the stack is not empty, we're going to do the same thing here. Oops. Return x. If I get something wrong, it's at the width calculation for sure. I just don't know if what just happened. Oh. Pop. Okay, yeah. Something's wrong. Oh, I think it's index minus stack.peak plus 1. Oh my gosh, why did I do that again? Yeah, because we have to take the difference between what we're currently trying to calculate and then where we are now, and then we plus 1 because it's 0 indexed. Or not. Is it minus 1? See, I'm just guessing at this point. We're gonna have to brush that up. It is, okay. Largest rectangle in what? What is it called? Largest rectangle in what? In histogram. Understand width calculation. Yeah, I don't really understand why we subtract 1. Okay. This is what I'm talking about. Like, I know that hard problem. I know how to solve it. I just can't. I can't explain why that width calculation is what it is. Binary search, our favorite. Okay. While left is less than equal to right. If num's middle. Middle. Yeah, if we don't find it, yeah. Okay. Cool. Nice. 2D matrix. This is the same thing. This is the same thing. It's just you have to iterate a different data structure to get it. Right minus left by the 2 if. Oh, no. I'm messing up. Equals. I mess this up quite often, calculating the row and column. So you take the middle value, the row will be the middle value divided by the length of the x-axis, and then the column will be the middle divided by, or the remainder of the x-axis, I think. If I get this wrong, it's because I mixed those two up. Minus 1. Yeah. Let's see if I got it right. Yeah. I'm pretty sure. I'm pretty sure I got that right. Oh, I forgot time and space. Okay, well, this is all binary search stuff. So space for binary search was constant, so O of 1, and then time was log n. This is the same thing. I hate this problem. I'm gonna have to write a note for this one. 1. So max equals 1 for the bananas in each pile. Max equals math.max between max and bananas. So we have to calculate the minimum and maximum. These are speeds. We have the minimum speed, which is 1 banana per hour, and then the max speed, which is the largest amount of bananas per hour. And then what do we do? While min is less than max. See here, I don't know if it's less than or equal to. I believe it's less than. Yeah, my educated guess is less than, and it's because the output will be dependent on the left and right, or the min and max pointer converging over each other. So I think it's I don't think it has the equal to. I don't think it's inclusive, I guess. So you have to find the average speed, and then for each pile of bananas, hours plus equals the rounded up version of yeah. Okay. So if the time it took us to eat the bananas is less than or equal to the time we want to eat them in, then we make right equal average. And so this, if we meet this condition, that means we're eating it too fast or just the right speed. And if we don't, then we do this. We need to be eating it faster. And return right, I believe. Oh, shoot. Max. Min. And then we're going to turn max. See, something's wrong. Is it equal? Is it equal? Was I wrong the whole time? No, infinite. It's infinite. Wow. What am I doing wrong? Let's see. What am I doing wrong? If ours is... That means we're eating it too fast. So we need to slow down, which is what this does. Is less than or equal to. I don't know. Fast. So we need to slow down. Ours is less than. So if we ate it too fast or just right. This is so tricky. Doubt it's this. I'm just shooting in the dark too at this point. So, I don't know. Yeah, see, this is gonna be infinite. Yep. What am I? Oh, man. Okay, let's make sure I'm understanding this right. Yeah, see, that's a disaster. Oh my gosh. plus. Oh. Wait, is it because I'm not casting? That totally could be it. Because it's just doing integer division. Oh my gosh. That's crazy. I knew I was doing the thing right. Okay, wait, actually let's see if we pass all test cases. Oh my gosh. At least I caught it. There you go. What's faster than this? But I don't. Quotient. What the heck? I think this is sufficient. I don't need to write notes about this. I think I understand it well enough. Finding the minimum. So, oh wait, space for this. What was space for this? Space is constant. Time is n log n, where n is the amount is the size of piles. Yeah. So space is. I think I have that right. Space is constant. Time is n log n. Is it optimal? Let's ask if it's optimal. Okay. N log max. What's max? Oh yeah. Okay, cool. Is this the most optimal solution? So it is, okay, it is optimal. Cool. Let's find minimum in sorted array. Or rotated sorted array. So, how do we do this? We need our pointers. Going to be less than or equal to because we're searching. We need to calculate middle as always. So we need to check if I think the solution is checking. No. The solution is checking. We need to find where the rotation is. Yeah. Because wherever the rotation is, that's where our minimum value is. So if the left side is not rotated, then right equals middle minus 1. Left equals middle plus 1. Actually, I lied. It's not less than or equal to. Because it's dependent on converging. I think. Is this it? Do I have this the wrong way? Maybe if it's sorted. If it's sorted, then we do... Oops. Yeah, if it's sorted, then we do it. Because if we're in a sorted portion of the array... Oops. Then... if we're in a sorted portion of the array... then that portion is not where the minimum is. Was I thinking about it wrong? Don't tell. If this fixes it. Oh my gosh. Okay. Because lefts could definitely be... Oh, I'm doing this all wrong. Okay, let's restart. I think I know what's happening. So while left is less than right, middle equals left plus right minus left. Left divided by 2. If nums... Oh, no. Nums left is greater than nums middle. Am I doing this right? If we're in the unsorted portion of the array. I'm not doing this right. Does that change it? Why would that change it? Oh. I keep on saying, oh, as if like I'm gonna get it right. Maybe it is left. What am I doing wrong? I know this. I know this solution. I don't know why I don't think you increment both because then you'd forget. Yeah. If this is the case, that's what I'm saying. I think it's... What? Wait. Am I returning index? No, I'm returning value. Yeah. Okay. Thank God. I thought it was like. So 5. If this portion is sorted, which it is, then we know it's on this half. 1. This is kind of messed up. I think I tried this already, but. Yep. What? What am I doing now? The left, no. So if it's not, if it's on the rotation. Yeah, we can guarantee that because then we know middle is less than nums. But we could be passing it is what I think. Yeah, I'm looking at the solution. I don't understand this. Did I not try that? So we find the unsorted portion. No, we find that. Yeah, unsorted portion. And we go to it. Oh. Did I flip it? That's breaking. Okay. I don't know why I don't understand this, because I thought it was pretty straightforward. Of course. Okay, we're adding that to the understand solution got wrong. Oh my gosh. That's fascinating. Okay. That's that's not encouraging. I think I know this one. Okay, so we calculate the middle. And then if the value that we're at equals the target, then I'm going to return the index, because this is indexing, right? Yes, it's indexing. If it's less than target, oh, this is like 20 if statements. All right, so if it's less than target and the left side is sorted, so if the value we have is less than the target, and the left side is sorted. No, this is so wrong. So if the left side is sorted, and target is less than the left, or target is greater than the middle, then we don't want the middle we don't want the left portion. And then we do the opposite here. And if the target is less than arms middle, we do the same thing here. Arms right, left equals, oh wait, no. Right equals middle minus 1, else left equals middle plus 1. Yeah. And then we return -1, otherwise. Beautiful. There we go. See, I know this one. Search for minimum was tricky. I think this is a one-off because of that. Oh my gosh. Yeah, that's what I was gonna say. Oh my gosh, what the heck is this? Why is it even allowed to run, bro? Why? What does that even mean? Well then. What am I doing wrong? What am I doing wrong? I passed all but 3 test cases. Okay. What am I doing wrong? Target left, middle. help. What the? I actually don't know what I'm doing wrong. Like, I know what's going wrong in this test case, I just don't know how to fix it. Because it basically doesn't even see the 1. That's crazy. Alright, I'm looking at the solution. I have no clue what I'm doing wrong. Okay, that's right. Wasn't I getting errors by doing this? Right. Wait, what? That passed? Nums equals left. What? Your test case was failing. So 3, 1, it'll point at 3. Nums dot left. I see. Yeah, I'm gonna have to look more into that. Search and rotate it, sort of array. Y in y less than or equal to in condition. I don't really know that. Also, another thing is, like, people say generally, like, with mediums and, like, easy should be what, 15 minutes, medium should be 30, and then hard should be 45. Generally, like, if I don't know the solution within 15 minutes of thinking about it, and at least if I don't start typing within 15 minutes, like, I just waste another 30 minutes doing the problem. And I've found that generally to be the case because, like, I'm thinking about it. I'm trying to, like, actively problem solve it. But if I don't start typing, then I'm cooked in terms of trying to find the solution. So yeah, that's the situation. So that's why I'm not really necessarily afraid to look at the solution, especially if I'm, like, writing this list down and I have stuff that I need to work on. Yeah, I don't have a problem with looking at the solution early, even though some people may think it's premature or something like that. Okay. Time key value store. See, this problem is fine. Actually, I'll go over the weird thing afterwards. So what do we need to do? I think we need a hash map. We always need a hash map. String pair, or no, it's a list of pairs. Map. List.map equals new hash map. Public string value. Public int timestamp. Yeah. So we have to keep a hash map of the keys, and then as value timestamp, or as values are added to that key, we keep track of a list of the timestamps, and then we'll binary search through that list, basically. So if map does not contain the key, map.put key new array list, and then map.get key.add new pair value timestamp. So the tricky part about this question is that, oh wait, I didn't even read this. This is where reading the constraints is so important. When I first did this problem, I didn't know that all the timestamps were strictly increasing, which I don't know why I assumed that they weren't, but yeah, remember to read the constraints. Okay, if map does not contain the key, return, otherwise we're going to return binary search for map.get key and timestamp. Public string binary search list pair list and timestamp. And left equals 0 and right equals list dot size. Yeah. While left is less than right. I think it's less than or equal to because we're trying to search for a timestamp. And middle equals left plus right minus left divided by 2. If middle if list.get middle.timestamp equals timestamp, then we're going to return list.get middle.value. If list.get middle.timestamp is less than the timestamp we're looking for, left equals middle. Yeah, that's it. Oh, contains key. Beautiful, beautiful, beautiful. Okay, space complexity. Well, we have to do it per function. So space technically there's, So this set occurs in O of 1. Get occurs in log n. Yeah. And then actually doesn't, yeah, set, so that's time. But for space, if we include map, then set can take O of n, and then get is still log n. Okay, let's actually ask GPT. I wonder what GPT will say about this. What is the space and time complexity of this? Yeah, I am really curious. Because I think you have to do it per function, yeah. So set adding to the list. But what about adding like, oh wait, that's time complexity, yeah. I got that. Yep. Okay, space complexity is yeah, okay. So time-based key value store. Time-based key value store. Understand space complexity. It's not like too bad, but I didn't really think of the space complexity. So it looks like it describes space complexity as a whole, which makes sense. As like the data structure itself, because it's a data structure, right? Yeah, the time map data structure. This problem is terrible. Okay, so we have to get the first length, nums1 length, second length, and then total length. And if the first length is greater than the second length, then we're going to switch them. Because we will be doing binary search, and we want to do binary search on the smaller of the two arrays. Yeah. So now we have to take left equals 0 and right equals length 1. And we don't do -1 because we're appending the two arrays without, like we're virtually appending the two arrays with not actually appending the two arrays. Equals total. So we want to do that because we want to round up a while. So right, is it less than or equal to? This is the median of two. What happens when they converge? I think, yeah. I might change the left or right. I need to figure out the rest of the problem though. So we want partitions. We want to partition both of the sorted arrays. So this is the traditional halfway point. Partition 2. This is the halfway point minus the first partition. Then we need the first left pointer, which is one partition 1 minus 1. I'll explain this later. So partition 1, so because we're partitioning these two arrays, if we've reached 0 on one of them, then we want to give it a theoretical minimum, like an infinite minimum, because that portion of the array is as far as we go. I did not explain that clearly whatsoever, though. Wait, am I doing this right? Let's figure it out. Oh, shoot. I do need to work on, like, I understand how this works. I don't think I can clearly explain it, though. Partition. Oops. My gosh. Oh. It's this. Something's wrong. Of course. Okay, so there are two things. I don't know why we do less than or equals to fully. Median of two sorted arrays. Why? Understand why we do less than or equal to, and be able to explain better. Yeah. Okay. I got it though. That doesn't mean much if I can't explain it. I know how to do it, I just can't explain it though. Okay. Something was next. Okay, I need to go to the bathroom. I need to do something real quick. I need to get more water too. Okay. Okay. Am I even live? Something's not loading. I'm like afraid to reload this though. Oh. Okay, I am live. Cool. YouTube Studio was messing something up. Okay. So we're only on binary search. Oh my gosh. All right. Let's get back to work. Because how do we do this one? We have to keep track of a minimum price. And then we have to keep track of our current profit. So this has to be max value because we need a minimum to begin with. Yeah, if the price is less than the minimum, then the minimum is now that price. Profit is the max between profit and price minus min. Okay. Whoops. Time complexity is O of n, space complexity is constant. Okay. This one actually, I know that I don't fully understand one line of this. So we have a left pointer, and then we're just gonna have length, and then so right has to be less than the length of the string. So if I need a hash map too, I think. Oh my gosh, stop. I'm gonna change that next time. So map character integer. So this is kind of like TwoSum where we store previously iterated characters and their corresponding indexes in a hash map. Maybe I do understand this. So if the map does not contain, oh wait, actually, we have to get the cur. So if the map does not contain the key cur, or no, if it does contain it, then we need to reset the left pointer because we have encountered a duplicate character. And it's going to equal the max between what it currently is and what are the previously iterated indexes. Plus 1. And then length is going to equal math.max between length and right minus left plus 1. I think because it's 0 indexed. Yeah. And then map.put cur. Right. So why? This is the line I'm confused about, line 10. I don't necessarily know why we do that, but maybe I can quickly figure it out. I don't think it's that hard. Yeah. Yeah, okay, so I don't know the situations where left would be greater than, or sorry, this would ever be greater than left. Because we go A, what's the first one we have? A. First double is A. So left would be 0. And so would mat. Oh. So this iterates, this gets rid of it. But what's the situation in which, okay, so I get the situation in which we follow this path, but what situation do we follow this path? Oh, it's when we previously, or it's when we've run into another duplicate and that duplicate is further past than the current duplicate we ran into. Ah, I see. That was easy. Okay. Longest repeating character replacement. So left pointer is 0, right pointer is also going to be 0, while right is less than s dot length. We also need a frequency chart or tracker. So we need to track the max frequency and have a frequency array because we need to keep track of the character that has the most frequencies, and then subtract k from it to calculate the answer to this problem. So we'll take freq s.char at right minus a, increment it, and then max freq will equal the max of max freq and that value. Oh wait. Yeah, that value. Yeah. And if right minus left plus 1, so the current length minus the character with the biggest frequency is greater than k, which is the amount of replacements we get, then we're going to, I think this is while too. We're going to take the left's character and decrement. Okay. Yeah. Left plus plus. I think that's it. And then output equals math.max output and right minus left plus 1. Return output. I think that's it. Uh-oh. Oh, I'd never increment right. Whoops. Oh my gosh. Let's see. There we go. Permutation in string. Which one is this? Oh, bro. This is just a sliding window anagram, which is dumb. So if s2.length is less than s1.length, we have a problem. New inst 26 freak 2. Lowercase English letters. Whoops. Beautiful. What's the... It probably doesn't do the comparison or something like that. Yeah, bro, like, I'm not worrying about... I mean, my space complexity is the same. I just iterate. That one iterates fewer times. Yeah, I'm not tripping over that. So space complexity is constant. Time complexity is O of n. This is O of n. This is O of n. This is O of n. Where n is the length of S2. Yeah. You know, I'm gonna double check because I have a feeling I might be wrong. What is the... Huh? Oh my gosh. Yeah, okay, we're chilling. Minimum Windows substring. Oh my gosh, dude, this ROM is terrible. So if t, this is the same thing, if t.length is greater than s.length, we got a problem. And left. There's also something else. Oh, yeah, I need. Okay, so we have a frequency array that has all the characters in T, and then we have a left pointer, right pointer, our minimum start pointer, our minimum length, and the required characters that we have to satisfy, the required number of characters that we have to satisfy. So while the right pointer is less than s.length, we're going to take the frequency array, take s.char at right, and then decrement it. And if that value that we just decremented equals 0, then we're gonna decrement required. So if we've taken one of the letters that we have in T and we've satisfied both of them, or the number of those letters, then we're going to decrement the amount of required letters that we have to. Oh wait, actually no. Sorry. All that's the same, but if this is greater than 0. And then right, plus, and then while required is 0, actually before this, if right minus left plus 1 is less than min length equals right minus left plus 1, min start equals left. I have a feeling this might be wrong. Yeah. I think I know why. There we go. Yeah. Because I was modifying I was making it 0 before I checked if that was one of the values that we needed. So, or I was modifying the value that I needed to check before I checked, or before I checked it, not after. So yeah. So we do a sliding window technique where we basically just sliding window until we hit, sliding a window until we have all the values that we need, and then as soon as we remove a value, yeah, sliding, yeah, it's just like a expanding and contracting window like this. Like, I gotta do it this way. Like boom, 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 boom. And then we track the min length as we do that. I hate that problem. Honestly, I dislike a lot of these sliding window problems. Including this one. Because this one I think you have to use a deck. Why? I actually don't think my key mappings are off. I think I'm just used to Windows. No, that doesn't matter actually. So if the current index is great, the current index minus the end of the sliding window is greater than the size of the window. Is it -1? Is there a one-off error? That'll be length 2. So 2 minus 0 is length 2. 3 minus 1 is length 2. So yeah, it's even though. Okay. Deck dot poll first. And this is peak first. Yeah. And then while the deck is not empty, and deck dot peak last. I think nums. Oh, I know exactly why it's breaking. My keyboard, not this. While the last number is less than deck.poll last. minus peak first. What am I trying to do? I need my output array. It's what nums, really nums dot length plus, or minus k plus 1. So if I if I is greater than or equal to k minus 1, yeah. I'm pretty sure it's peak first, but what makes sense to me is peak last. My condition's wrong. K minus 1 is 2. Well, I is greater than or equal to 2. That makes sense. I minus k, 2 minus 3 plus 1, 0. What? What line is it breaking at? 18. This is breaking here. It's a one-off error? No. Oh my gosh. That's why. Okay, I'm almost there. Yeah, see. Okay, so why is it peak first? So this condition is if we're over the size. If we're over this, if we're over k. If the deck is over k, we do this. If the current value is larger than the I still don't get why this peaked first. Like, yeah, I don't really understand. Because aren't we? This makes me think that we're adding the largest numbers last. Oh. I'm thinking about it the wrong way. So this is to take care of whether or not we're over the size of k, and this is to make sure that we're only storing values that are, this is to make sure we drop values that are smaller than our current value. And then we offer that to the last part, and then because of that, we peak first. So we're always storing the largest at the first in the front end, and then in the back end, we are always, we're always just picking off the smaller ones. Okay, that makes sense. Okay. Linked list. I really like the linked list props. They're pretty good. So here we make so I figured I'd do space complexity, space and time complexity for the other one too. Space complexity was definitely, space complexity is technically K, I think, because, wait, oh wait, what the heck? This is the wrong one. Space complexity is K, which is the size of the window. Time complexity is O of n. It's O of n. Yeah. Stack operations O1, yeah. Space complexity is n? I forgot about the output array. Yeah. Okay. Yeah, so this, we just take the head. The best way to explain this is to draw. So basically we have 1, 2, 3, or actually 1, 2, 3, 4, 5. And basically what we do is we do this. Boom, we cut this off, and then we reset here. And then we do boom, we cut, and then this is our new head. And then boom, and we keep on doing it. So yeah, they submit this. Okay, cool. Next list. Merge two sorted lists. Okay, so we're gonna create a new list. We're gonna create a dummy, and then oh wait, no. Yeah, we're gonna create a dummy. So then while list 1 is not null and list 2 is not null, we're going to say, okay, the next pointer for list is going to be, oh no, actually before we do that, we have to check which value is smaller. So if list1.val is less than list2.val, then list.next equals a new list node with list 1's value. And then list 1 equals list 1.next. We have to iterate. And yeah, I think that's it. And then we do the opposite here. when we iterate the actual list. And then if one list is longer than the other, we have to take that into account. So list.next equals new list node, and we just copy here. 1 equals list1.next, and then list2 equals list.next. And we do the same for list 2. And then we return the dummy.next, the dummy pointer. Yeah. Space complexity, O of n. We're creating a list node every time. And then time complexity is O of 1, or O of n as well. Let's see how it works with list nodes, though. I'm not exactly confident in my answer. What is the space? Okay. Yeah, the same thing. O of n is in like the sum of both the lengths, I guess. I guess I have to be more specific than that, though. Yeah, auxiliary space is O of 1, right? Yeah. Cool. Oh my gosh, this one's like annoying. So we have a slow pointer, which equals to the head. We have a fast pointer, equals to the head. And we have to find the halfway point. And we do that by iterating slow once and fast twice. Now, when we find the halfway point, slow will be on the halfway point. So, what do we do? Let me cut off the branch. Cut off the pointer. Oh wait, it's this. So basically we find the halfway point, we cut off we split the linked list. So we have the second half and the first half is in head. And now we have to reverse it. So while cur does not equal null, list node next equals cur.next, cur.next equals previous, previous equals cur, and cur equals next. And then now we need to merge back the lists. So list node L1 equals head, list node L2 equals prev, and while L1 does not equal null and L2 does not equal null, list node temp1 equals L1.next, list node temp2 equals L2.next, L1.next equals L2, L2.next equals temp1, temp1 equals, no, L1 equals temp1, L2 equals temp2. There we go. So space complexity is actually O of 1 because, actually is it? Space complexity here is O of n. Oh, it's O of, n divided by 2, which is still O of n. This is, yeah, so space complexity is O of n, time complexity is O of n. Let's double check though, because this is tricky. Oh my gosh. Send. Okay. Is it next? What about next? Isn't this node next? See, I think even if I ask this, even if it's wrong, it's going to tell me that it's right. Or that I'm right. Linear space. Why not? I don't get it. I'm adding it to the list. Oh my gosh. Okay. Slow equals. Yeah. Okay. Time complexity is O of n. Space complexity is not. It's just pointed. Oh, is that why? We're not creating more space. We're just reassigning pointers. Okay, that's why. I can just get rid of this then. Actually, I'm just going to keep it there just in case. Okay, there are two ways to do this, and I'm going to do both because I think they're both important. So you can use a hash map. Oh my gosh. And basically, you literally create a mapping. Also, the fact that they use node instead of list node, and they use list node in every other problem is really annoying. Like, that's super dumb. Head while cur does not equal null. Map.put node, or no, cur new node cur.val. Cur equals cur.next. And then while or I'll do cur equals head while cur does not equal null. If cur dot random does not equal null, cur dot or map dot get cur dot random equals map dot get cur dot random, and then map dot get cur dot next equals map dot get cur dot next. Cur equals cur dot next. Return map dot get cur. So basically, of course, what did I do wrong? Wait, what did I do wrong? What? Oh. Okay, yeah, so basically we're iterating through the list linearly, creating a new node for that value and mapping it to its original node. And then we reiterate linearly, and then we use the hash map to get the random pointers and the next pointers. The next pointers are easy, but the random pointers are harder. And then we have to add this null check because there's always one random pointer that goes null. So that's how you do it with a hash map. But there's a way to do it with constant time. And you basically, what do you have to do? So you take cur, you make it head, and then you say while, and then you iterate it while cur is not null, and then you store the next node, and basically you duplicate it. So instead of 7, 13, 11, 10, 1 null, it's 7, 7, 13, 13, 4, 11, 11, 10, 10, 1, 1. So then cur.next will equal new node cur.val, and then cur.next.next equals next, and then cur equals cur.next.next. That's kind of complicated. Basically, store the pointer for the next node, duplicate this node and attach it to the next. Now it's been cut off. Assign the stored next node to the duplicated node, and then iterate to that node. And then cur is going to equal head again, and then while cur does not equal null, we're going to assign the pointers. So if cur.random does not equal null, cur.next.random, which is the duplicate one, equals cur.random.next, which is the duplicate one for that random pointer, and then cur equals cur.next.next. So now we have all the pointers assigned, and we just have to detach. So while, what are we doing? Cur equals head again, and while cur does not equal null, cur equals cur.next.next. If cur, oh, actually, so cur equals head, and then node copy equals cur.next, and then node copy head equals cur.next. So if copy.next does not equal null, and copy equals copy.next equals copy.next.next. And I need to do that here actually as well. So then after this we do cur equals cur.next, copy equals copy.next, and then we are good. Copy head. So this is nice. This is O of 1 space, but O of n time, which is faster than the other one because we don't use a hash map. O of n time. O of 1 space. Beautiful. Okay. Add two numbers. This one's pretty easy, especially because we add them in reverse. So we have to create another list node. So while L1 does not equal null and L2 does not equal null, I actually need another value here. So if so list.next is going to equal a new list node with L1.val plus L2.val plus remainder divided by 10. Oh, no, mod 10, yeah. So we want to get the single digit addition basically, and then remainder is going to equal L1.val plus L2.val plus remainder plus itself divided by 10, and this is how we're carrying over our value if the addition is double digits. It's L1 or list.next. L1 equals L1.next. L2 equals L2.next, and then yeah, that's good. So now we have to handle if L1 or L2 is longer than the other. So L1 does not equal null. We'll start with L1, and you just do the same thing. This node L1.val plus remainder to mod 10. Remainder equals L1.val plus remainder divided by 10, and then list.next. L1 equals L1.next. And then you do the same thing for L2. This node, L2.val plus remainder. And then you have to tack on the remainder, because the remainder, if we end on an addition or a summation that is larger than 10, or 10 or larger, then we need to be able to do that. Or we need to be able to add it back. And then we return dummy.next. So this is O of n time. Oh, no. It's O of n where n is the larger of the two lists. And then, so I guess it's O of max n m, like this, like that. Space. Let's see. We are creating a new list node every time. I'm kind of confused on whether or not that counts as space. What's the time or space complexity of this? Yeah, I don't know. See, I was right there. Okay, space is the same thing. Auxiliary is one though, so I have to be careful about that. I need to do more research on which one's more important. I think auxiliary is though. Add to linked list cycle. Okay, this is cake. So we're going to create a slow node, fast node, and then while fast does not equal null and fast.next does not equal null, we're going to iterate slow and fast twice. And if slow ever equals fast, then we have run into a cycle. And if we ever exit this loop, then there's no cycle to begin with. O of n time, O of 1 space. Just like that. Find duplicate number. Oh, this is like the Floyd's like tortoise and hare algorithm or something like that. And you have to like do a do while. I've never needed to use a do while ever. Int fast or int slow equals num 0. Int fast equals num 0. I know the proof for this too. It's kind of complicated, but it does exist. Slow equals slow dot slow nums slow. Fast equals nums fast. So we're iterating twice when we're doing fast. Slow does not equal fast. And then while you have to reset it. Slow equals nums 0. While slow does not equal fast. Slow equals nums slow. Fast equals nums fast. Return. It doesn't matter if it's slow or fast, they'll be the same. Cool. So space is O of 1, time is O of n. That one's pretty easy too, I'm not going to check that. LRU cache. Okay. Let's see. I need to change something real quick. Okay. Cache. Honestly, like this one is kind of, if you think about this, if you solve this first try, I'm kind of crazy. Positive size capacity. So anytime we manipulate or touch or add a value, they reset how recently used they were. And then if we exceed the capacity, then we want to get rid of the least recently used value. So the first thing I'm going to do is store capacity in this field. And then store this stuff, left, node right. Map node no. I think that's it. Yeah. This dot capacity equals capacity. This dot left equals new node. This dot right equals new node. This dot left dot next equals this dot right. This dot right dot prev equals this dot left. This dot map equals new hash map. Okay, and then we have to create the node class. Public int key, public int value, public node, int key, int value. This dot key equals key, this dot value equals value. Yeah. Yeah, so basically, what are we doing here? We're creating a doubly linked list, and these instance fields of left and right, they're basically pointers for us that aren't a part of the list, but we use them to determine what's most recently used and least recently used, or to add, or to insert and remove. So, yeah, get. How do we get values? So if map.contains, if map does not contains, this map.contains key return -1. Yeah, else. We have to return this map.get key value. Yeah, and this is spelled wrong. Oh. But we also have to remove okay, public void remove node, then public void insert node. So if we remove, what happens? Okay, so node prev equals node.prev, node next equals node.next, prev.next equals next, next.prev equals prev. And then here we're inserting node equals this dot right dot prev, node next equals this dot right. So then it's prev.next equals node, prev next dot prev equals node, and then node.next or prev equals prev, node.next equals next. Yeah. So that's that. Now pudding. So if this dot map dot size equals this dot capacity, if we're at capacity, I think I'm thinking about this the wrong way. If we have the key, if we don't have the key, no, if we have the key, then map.get, we have to get the node, or get the node, and then node.value is reset, and then we remove that node and then insert it again. And then if this dot map dot size equals this dot capacity, if we're at capacity, then we have to take the LRU, which equals this dot left dot next, and then this dot map, we have to remove it from the hash map, and then remove it from the linked list, and then get the new node, and then add it to the map. This is also outside of the. Yeah, it's like this. So I think for the most part that's right. Oh, whoops. Cool. Okay, so overall space complexity for the LRU cache, it's going to be O of n because of the hash map, and I believe because of the node, the doubly linked list. The time complexity of get is going to be O of 1. Removals and insertions are O of 1. That's O of 1, yeah. And then that's O of 1. Put. Speed of put. O of 1, 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 O of 1. So everything's O of 1. Let's ask GPT. Yeah. Yeah, O of 1, space. Capacity. Oh, that actually makes sense. Wait. Yeah, see? O of n, where n is the number of insertions. Yeah, okay, cool. I'm okay with that. Oh my gosh. Oh, this one's actually not bad. But you have to use a priority queue. I don't know the space complexity of priority queue, so I'm not gonna even try to guess it. That's something I'll write down. But basically, you take a priority queue, and then you add each of the heads of the nodes in there, and it'll order it in increasing order. And then while node output equals new list node dummy equals list. While queue is not empty, list.next equals queue dot poll. Oh wait, no. List node cur equals queue dot poll. List.next equals new list node cur dot val. If cur dot next does not equal null, we're going to take queue and offer cur dot next, and it'll automatically sort. And then list equals list dot next. And then we're going to return dummy.next. Oh yeah, null exceptions. See, why would you have an array of list nodes and one of them would be null? That doesn't make a lot of sense to me. Oops. Cool. So let's time complexity, that's whatever the sorting mechanism, whatever the min heap algorithm takes. Space complexity is equals m times n, where n is the number of lists and m is the average length of those lists. Yeah, let's see. N log k. Is adding really log? It says n log n. Okay, that's what I'm adding. Merge k sorted lists. Understand priority queue, time complexity. And space complexity, time and space. Just generally big O for that. Okay, that's done. This one sucks, like a lot. Okay. So if the head is null, or if k equals 1, we're going to return the head. Because if k equals 1, then if each group has to be 1, you can't reverse each group, so it's just the original list. If head equals null, then return null. Now what? So we have to have a dummy variable. Yeah. And then we have to have a group head. So this will be the head of each group that we want to reverse. And then we have to attach the original list and get the size of the list. So we could do this. We'll just get the size of the list, and while size is greater than k, we're going to perform the reversals. So we have to get the next node, which is going to be group head.next. And then we have to get the node that we want to move to the front, which will be next.node.next. For this is 1 actually. So the reason why we do 1 is because, I could be wrong, but the reason why we do 1 is because if we want to reverse a group of 3, we only need to move 2 nodes. Yeah, that's why. So first step is to detach the node to move. So next node dot next equals node to move dot next, and then we need to reassign the we have to make node to move the first element in the group. Make node to move first element. The reason why I have to write these comments is because it actually helps me think through these, because this is actually a really complicated algorithm. So we have to take the group head dot next and no, we have to take node to move dot next and make it group head dot next, because yeah. And then we need to, so we've detached the node to move and then reassigned its pointer. Now we need to what do we need to do? We need to make the node to move the first element. Wait. This goes here. Whoops. This is actually reassigning node to move's pointer. This will make node to move the first element. Yeah. And then the last step is to get the next node to move. So get the next node to move, which would be node to move equals next node dot next. And then after all of these, we make group head equal to next node. We reassign the group head because we've reversed the entire group, and then we decrement size by k. Then we return dummy.next. Oh my gosh. Dude. There we go. So time complexity is going to be O of n, where n is equal to the amount of nodes in the list, and space complexity is going to be O of 1. It could be O of n actually, because of this. Yeah, I really need to dial down the space complexity for linked list problems. That's a general note that I'll probably have to have. Yeah, that makes sense. Bro, tell me, like, why doesn't it tell? What's the point of splitting these two? Actually, oh, I'm the dumb one. Never mind. Yeah, okay. Bet. Cool. Bet. We're done with linked lists. Okay, wait, actually, do I have that written down? Generally need to understand space complexity surrounding I can't spell. Oh my. Linked lists. Cool. Inverting a binary tree. So there's no way we're gonna return that. And then we got left equals left, we got right equals right, return root. Okay, so this occurs in O of n, where n is the number of nodes in the tree. Space complexity O of 1. Oh my gosh. I didn't mean to do that. I meant to do this. Okay, max depth. Did not even know that. Okay, I'm gonna have to do that. Like I don't know the space or time for trees either. Generally just like recursion too. Like once we get to backtracking, I'm not gonna know what the heck I'm doing. Okay. So if the root is null, we're gonna return 0. And then we're gonna get the lefts. And return 1 plus math.max left or right. Yep. So we're just counting each left and right leaf or subtree, and then calculating and just like returning the max one. We're literally just going from the bottom to the top and iterating and counting. Time complexity is O of 1. No clue about space complexity. Okay, diameter of tree. I hate this problem. We have to get the root. If the root equals null, return 0. Actually, this can be void. No, I can't. Actually, I need the return values. So find the length of the left. It doesn't include the current node, which is kind of dumb. Actually, would it even be a problem if it included the current node? I don't think it would. Maybe that's why this is a problem. Cool. Yeah, I'm just like most of this time complexity, so that's O of 1. I'm not going to do space because I have no clue about space. Did I do the right one? Diameter balanced. Okay. Angle left equals DFS. Basically, we're returning exit conditions. -1 is our exit condition, and then we return the depth. Cool. Space or time O of 1, space. You know the deal. Same tree. Same tree. So if P equals null or Q equals null, return P equals Q. So if either of them are null, they both have to be null. If P dot val does not equal Q dot val, we're just going to return false. And then we're going to turn recursion for that. Make sure it's an and, because we want both sides to be the same. Cool. Times O of 1. Or sorry, O of n. What am I saying? O of n plus m. Or P plus Q. Oh, no, it's just P. Oh, no. Time complexity is O of max P or Q. Because if it's not true, then we have to iterate the entire, or mostly the entire. Actually, I wonder what GPT is going to say about this. Oh my gosh. What are we doing now? Subtree? Cool. What does this say? Time. Oh, that. Yeah, the smaller of the two trees. Because once you hit a failing condition, okay, so it's the opposite. Because once you hit a failing condition, it's just going to like exit everything. So if the subroot, yeah, the thing about this problem too is like they don't tell you that if you have a subroot that's null. Well, actually, I guess it doesn't tell you that if you have a subroot that's null that counts as a subtree, because I guess it's implicit, like all of these have null children, all of these leaves. I'm not going to blame Leetcode for that. Return true if root equals null and the subroot equals null, or and the subroot doesn't equal null, then we can return false. Now what? Oh, if root.val equals subroot.val and is same tree, root subroot, return true. Otherwise, we're going to return root is subtree of root.left subroot, or is subtree root.right subroot, because we only need one of them to pass. And then we basically have to rewrite his same tree. Yeah. Okay. This should work. I'm actually curious about time complexity though. I think because we had the worst case, we go through each permutation of the root or each child of the root, and we run is same tree on all the roots, all the children. So is it? I think it might be like, oh, actually, wait, did I get it right? I didn't even check. Yeah, I did. All right, I think it might be big O of n times m, where n is the size of the root and m is the size of the subroot. Yeah, this one's an interesting one, actually. Maybe I'm just being dumb about it. So I wonder what space would be weird too, because you recursively call twice. Oh no, there are 3 recursive calls. How many subproblems are there? Because you have to do the recurrence relation on that. They're 2 to the 2. Yeah, that's weird. Space complexity is O plus M. Interesting. Yeah, time complexity is O times N. There you go. Okay. Oh, this problem's cake. So if root equals null, we're going to return null. And then while root does not equal null, if root.val is less than p.val and root.val is less than q.val, we need to go to the right side of the tree. So root equals root.right. Otherwise, if root.val is greater than p.val and root.val is greater than q.val, we need to go to the left side of the tree. And if all of those conditions are met, then we just need to return the root. This is O of n, where n is the number of... Oh no, this is O of n log n, right? Oh no, sorry, log n. just O log n, because this is basically binary search. And then space is a constant because there's no recursion or anything like that. What is the space complexity of this? Okay. Oh, that makes more sense. Okay, height. Okay. I just did that one. Level order traversal. So we need the output structure. And then if the root is null, we return an empty version of that. And if it isn't, then we start level order traversing. So we have a queue that starts tree nodes. And then we offer it the root. And while the queue is not empty, we'll traverse. We have to get the size. Get the current node. If the current node is left, it's not null. Same thing with the right. And then I actually need the level. To add cur.val, and then output to add level. Return output. Yeah. Oh. Should be good. Time complexity is we have to traverse each child, so it's O of n, where n equals the number of nodes in the tree. Space complexity. What is? I'm just gonna say it's O of n. I think that's reasonable. Yeah, cool. We are good there. Oh my gosh, my mouse is just like breaking. I've been staring at a screen for too long. Oh yeah, after I finish trees, take a quick break, like a 5-minute break. Maybe a little longer. Right side view. Okay, right side view is the same as the level order traversal, but we just add the values that come to the end of the size iterations. So equals new array list. If the root is null, turn the output. Tree node. Root. And while the queue is not empty. If what do I do? Oh, what do I do here? While the queue is not empty, size. Until I equals 0, I has to be less than size I plus plus. Cur equals q dot poll. Cur dot left. We still have to do all the traversals, or the entire traversal. Sorry. Q dot offer. Cur dot left. If cur dot right doesn't equal null. If size I equals size minus 1. I need to check something real quick. Okay, that's good. Okay, time complexities of n, because we have to do all the we have to traverse the entire tree, and then space complexities O of n as well. Count good nodes. This was a Google question at one point, like a really famous one, I'm pretty sure. Oh look, it's good. Look, solution. Start good equals 0. Do fast root. Integer dot mean value. Return. Start good. So we just need to do DFS, pass in the largest parent, and check each node against that parent, and then increment good based off of this dot good based off of whether or not the current value is greater than or equal to the largest parent. So yeah. So if root equals null, you just return 0. This, I think this can be void. This dot good plus equals. Wait, I forgot to add the second parameter. Int min. So if root dot val is greater than or equal to min, then we're gonna add 1. Otherwise, we're gonna add 0. And then min is going to equal the max between min and root.val. And then dfs root.left min, dfs root.right min. Yep. Cool. What was time complexity? O of n. Space complexity is whatever the recurrence relation is, because we're doing recursion. Okay, validate binary search tree. This one's fun. I like this one. So we just need to make sure this tree is a binary search tree. I think we just need to return DFS root and then long dot min value and long dot max value. Public boolean DFS tree node root long min long max. Okay. So if the root equals null, we're going to return true. If the root is less than or equal to, because I don't think only contains nodes less than, greater than, so it's exclusive. Min and or root dot val is greater than or equal to max. Return false. This has to be dot val. Otherwise, we're going to recursively call all this stuff. So root dot left. And once we go to the left subtree, we're going to make the root's value the max value. And we're going to do the opposite for the right side. And then max. Oh, there we go. Time complexity is O(n) on that. Okay. Validate kth smallest element. This one is pretty easy too. So what we'll do is we'll create a list. And then all we need to do is do an in-order traversal of the tree and then return list.get k-1 because it's 0 indexed. In order, tree node root list, integer list. If the root is null, we're just going to exit. And then we're going to do in order root list dot left, and then list dot add root dot val, and then in order root dot right list. That should be good. Yeah. Cool. This one's fun too. So a few things we need to do. For pre-order, the first element will always be the root. And for in order, first element will always be the root. And if we can find that value in the in order, we know what's on the left of it and the right of it. So 3 is the root here. We have 3. We find 3 here. Look, everything in the in order array, like physically in the array, everything to the left of it is on the left side. And everything to the right of it is on the right side here. So we can capitalize on knowing what the root is and what's on the left and right side to construct the tree using these two arrays. So the first thing we're going to need to do is to make a pre-order counter. Pre-order index. And then we will need to make an in-order mapping. Where index equals 0, this dot in-order mapping equals new hash map. That's a mess. Okay, so then we just iterate in order length plus. The only thing we need to do right now is the in order mapping. Dot put in order I. So we're Yeah, we're using the value as the key and the index as the value. And then we're just going to return build with a left pointer, a right pointer, and the pre-order array. So if left is greater than right, we're going to exit. That means we've finished that specific leaf. And then we get the root and recursively solve. So the root will be a new tree node that uses the pre-order index in the pre-order array, and then we iterate it as we go. And then we can establish the left subtree by recursively calling this. Left will still be 0, but the right side will be bound to the in order indexes. So it'll be, we're going to take the in order mapping and get this current root's value and get everything to the left side of it. And then we're going to throw in pre-order. And then the same thing with the right side. So then it'll be this dot in order mapping dot get root dot val, but +1 this time. We're going to use the right bound and then throw in the pre-order. And then we're just going to return root. And that should get us there. Yep. Time complexity. Prior overvan. This is overvan. Build. Yeah, it's overvan, in my view. Yeah. Time complexity is all bad. Space complexity, best case. I see that. Max path sum? Which one is this? What is this? Oh, I see. Okay, so I think an underlying principle about this problem is that if you just sum nothing, or you can sum nothing. So like if every node was negative, your max would be 0 because you can just sum one of the null children. Which I wasn't like aware of when I first saw this one. Path in a binary tree. Path in a binary tree is sequence of nodes. Node can only appear in the sequence at most once. Yeah. Path does not pass through root, pass sum. Okay. Yeah, it can't be like diameter. Like it can't go from 7 to 20 to 15. It has to be 7, 20, 15, which is 1, or 15, 20, and then whatever this is. But it can't be like 15, 20, 10 plus 7. Yeah. So if public max solution star max equals 0. DFS roots. Turn this time max. If the root is null, return 0. left equals DFS root dot left. But we're going to do like math.max, because remember, if the node is negative, 0 is still the best. I think that's why we do that, at least. I could be wrong. This dot max equals math.max between this dot max and left plus root dot val plus right. And then we're going to return root dot val plus math.max left or right. But okay, maybe I was wrong. Yeah, I'm definitely wrong. Oh no, maybe it's this. Let's see. Yeah, okay, I'm gonna have to look into that, because I don't think my reasoning that I explained before was the reason why we do this max stuff. So binary tree maximum path sum. Binary tree maximum path sum. Figure out why we do max child 0. Okay, cool. Bet this one's annoying. Okay. We have to do a helper method and then return string builder dot toString. Export serialize helper root string builder. Okay. If root equals null, string builder dot append will indicate a pound as null, and then let's helper root dot left string builder serialize helper root dot right string builder. String builder dot append root dot val dot append. Yeah. Cool. This one's interesting. So you take the queues string as lists, data dot split. I'm doing a terrible job explaining this. Okay, so to serialize it, we use the string builder, iterate in any way. I think this is dependent on whether you, like the method of iteration for serialization has to be the method of deserialization. So I'm just doing DFS. Oh, no, I'm not even doing DFS. I'm doing post order. Yeah, I should probably write that I honestly don't even know which traversal this is. I need to study the tree traversal methods. Yeah. But I think you have to you serialize the same way you deserialize. I think. I could be wrong. What do we do? Okay, so we have a queue now. And then we're gonna get string cur equals queue dot poll. The cur equals tree node root equals new tree node integer dot parse ints cur root dot left equals deserialize q root dot right equals deserialize serialize helper q. Gotta do that here. Return root. I think that's it. Yep. So, what's our space complexity here? Serialization is O of n, given that n is the number of nodes in the tree. Deserialization is also O of n. What is the time and space complexity of this? Okay. Cool. We've gotten through trees. Serialization, time complexity, O of n. Space complexity is O log O of n. Time complexity deserialize, yep. Cool. Okay. Was that the last one in trees? Yes, it was. Okay. I'm gonna take a break, like a quick break. Gotta check my texts. Okay. But I'm gonna go to the bathroom and grab a snack probably. Yeah. Hmm. Okay. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14? 14. Are they major? I mean, some of these are just, actually 15, 16, 17. One optional. These will take a while, I think. How many problems have we done? Let's see. 16, of course. Of course. The magic number. Okay. Yeah, I'm curious about how long some of this stuff's gonna take me. I don't even know if I'll finish the rest of this today. What should we do next? Tries or backtrack? I suck at backtracking. As you can tell. We'll see. We will see. Okay. Okay. Time to stop being lazy. Okay. This other screen I have is very distracting. I need to take my stuff out of the oven in like 20 minutes. Okay, I'll do tries and then I'll take my stuff out the oven. Okay. Oh my gosh, this is why we reset. Okay. What is it? Wait. Okay. So we have to make a root. And then we also have to make the try node class. String word public app character try node. Children. Hash map. Is that right? Well, we'll find out. Okay. So what was it? Oh, shoot. So we grab the root, and to insert, we have to add to the children. So we have to get the current character, and if the current node's children does not contain the key, then we have to add it. And then we have to iterate. And then at the end, the word will equal the word. And that's how we'll know we're at the end of the word. So when we search, what do we do? When we search, we iterate to. So to get the root, it's kind of the same thing. Node equals node.children.get or .char at I. If node equals null, then we return false. Yeah, that's it. And then we're going to return node.word equals, does not equal null. And then for the prefix, it's the same thing, but we don't add that null check. Or, yeah, that null check. Equals 0, has to plus prefix length plus node.children get or prefix.char at I. If node equals null, return false. Otherwise, we're going to return true. This should be it. Cool. So space complexity for the try data structure is going to be O of n, and then time complexity for insert is going to be O of n, where n is the size of the. Actually, wait. Space complexity. What does n stand for? N is going to be the average, or no. N is going to be the total amount of characters that are added to the tree. I don't know if there's a different way to represent that, though. Is there? Total length. Is there a different way to represent that? You could just say its space complexity is O of n times m, where n is the amount of words and m is the average length of each word. Time complexity for insert is O of n, where n is the length of the word. Search is the same thing, where n is the length of the word. Starts with is the same thing. Let's verify that, though. Yep, length. Yep, length. Yep, length. Yes, I did get it. Cool. Okay. These are all the same. I don't know, like, I guess they're different iterations of, yeah. Instead, this is how we represent the children. happens here. Yeah, I did this wrong. It's the old way of doing it. Yeah, that's all. I think that's it. Yeah. Okay. So space complexity is going to be the same, O of n times m, where O of n equals the number of words and m equals the length of words. Add word is going to be O of n time, and then search is going to be, worst case, search is going to be O of n, where n is, wait. Huh. I actually don't know. It's O of n. Oh, worst case is O of n squared. N is the length of the word. I'm worried about this, because technically the max would be 26. Yeah. I think it might just be O of n then. If it's 26. I'm going to say it's O of n space. Okay. Word search too. Oh my gosh. Time complexity. Okay. I'm gonna write this down. I think. What problem was that? Design and. What the heck? Who names this stuff? Design, add, and search words data structure. For everything. Okay, so we add everything into the, so we have a try. We add everything into the try. Add everything to the try. I'll be honest, I don't think I know how to do this. Oh, that's completely wrong. Oh my gosh. I didn't even I didn't think that was gonna work. That's crazy. Wow. Holy cow. Oh wow, that's wild. Oh my goodness. Okay, I need to, I need to go to my oven. I'll be right back. I can't believe I got it. That's kind of wild. Oh yeah. These will probably struggle with it a little bit. Okay, that's enough distractions. We gotta finish the rest of these. Kth largest element in stream. So, this is pretty straightforward. You have to, for this one, you have to make a priority queue. And you have to make it a max heap priority queue. And then size equals k. If you want to, I think you can do this too, just to make sure the size is right. So oh wait, no, it's not. It's actually not a max heap, it's a min heap. Yeah, so you consistently store large values in a min heap, and then you take the smallest value in the min heap. Let's see about this one. Given an array of integers. What's the expected output? What's this? Yeah, so max heap, we just get the absolute value of each of the stones insofar as the queue size is greater than 1, and then we return that conditional. I'm not going to do time complexity because I think well, now I need to write it. Study the time and space complexities of priority queue / heaps. Okay. This one's annoying. Yeah, this one priority queue. It's min heap, but just with coordinates, and then you add all the coordinates, create your output array, and then initialize all the values. Pretty simple. Okay, so largest element in the array. This is just a min heap. Okay, there's a faster way to do this, or is it just... Oh, they do use a max heap. I'm using a min heap. Interesting. Oh, this is... I'm not going to be able to figure this out. Yeah. I don't fully get how this works either. Yeah. You have to like keep track of each, like there's this thing called idles. There's a thing called idles that you have to keep track of. I don't even know what they are. And you have to be able to keep track of it as you iterate through all of these. Like even if I tried to do this, I wouldn't be able, I don't know if I'd be able to. We can give it a go. Like I don't even know if it's a min or it's a min. And it's not integer, it's string. Oh no, character. What am I doing? Character. Yeah, I don't really even know where to start. Yeah, just keep track of the idles. Yeah. I don't think I'm not gonna be able to solve this. I am curious. The thing is, I know what the answer involves, and I don't know how to get to that. And I don't even know how to start. See, I wasn't even supposed to start with a priority queue. You don't even use a priority queue. Like, I wouldn't have guessed that. Or even been able to get an educated guess. Yeah, like, it has a for loop with 2 conditions. I don't remember the last time I don't remember any time where I've written a for loop with 2 conditions. Yeah, that's interesting. Okay, so I honestly, like, I'm just gonna mark this as me not knowing it. Task scheduler. Scheduler. Understand solution. Did not know. I think that's the first. No, I did look at one other answer. Oh my gosh, my mouse is going crazy. Okay. Oh, that's unfortunate. Oh my gosh, my mouse. What is happening? Okay. Oh my gosh, yeah. I don't really know what data structures we need for this. Okay. Do I even need values here? I don't think I do. Oh, I think it's backwards. Oh my gosh. What am I doing wrong? Submissions. So So post. One, two, three, 4, 5, 6, 7, 8, 9, 10, 11. Am I missing something? Oh. Oh, that's why. That's why. I'm not incrementing index. There we go, beautiful. Okay, so space complexity is going to be, it's O of n for the number of users times, it's O of n times m where N is the amount of users and M is the number of tweets per user, like the average number of tweets per user. Post tweet, this occurs in constant time. So this is O of 1. Get news feed. This is going to be O of M times N, where O of M times, well, this is O of M times N, where N is the number of users and M is the average number of users or tweets per user, plus whatever, plus like X, where X represents the number of tweets the user has, but I think it'll reduce to M times N. This is constant. Unfollow, constant, or follow and unfollow are constant. Yeah. Let's check. Where's the space? Okay, post of 1, get news feed. T log T. I forgot about the priority queue. But what about... Oh, that's just... Yeah, they represent T as the total number of tweets, so that makes sense. Oh, 1, oh, 1. Okay, cool. Okay. Yeah, I'm gonna go over that when I go over space complexity for priority queues, and then we'll revisit this. Okay, but generally I got the right path there. This one's a fun problem, I think. Yeah, this one's pretty fun. Okay, that's done. Man. Okay, what do I do? I'm getting into uncharted territory here, so let's just start with backtracking. Oh my gosh. I'm gonna suck at all of these. Oh, see already. Actually don't. Okay. Yeah. Permutations. I'll be honest, can't explain how any of these backtracking algorithms work. Like, to a certain degree, I know how they work because I can solve them, but high level, no. there's no way for this to exit. How do I get this to... How do I get this to work? There we go. There we go. Cool. Oh my gosh. No, there has to be a loop. This is exactly what I did. Actually, it might be like this. So it's exiting too early. Yeah, I don't. What am I doing wrong here? I don't know. Time to look. Oh my gosh. That's the trick. Okay. Is it this? Yep. Okay. What is happening? What is happening? I still think this is an index. They're duplicates. How do I... If I remove the duplicate call... What if I do that? Huh. No way. Yeah. It's gotta be +1. Why is there duplicates though? Because maybe this is 0. Oh no. Yeah, I have no clue. I might be lost on this one. Okay. Yeah, let's see what I'm doing wrong. Oh, wow. I'm not really quite sure how this works. I had the right idea though. Let's see. Yeah, it has to be like this. What am I doing wrong? Oh. Double, huh? That's fascinating. It's all of backtracking. Yeah. Unfortunately, I don't know anything about backtracking. Okay. Well, actually... Too many. Well, let's see if this fixes it. Duplicates. I know what's wrong. I think. What? What's wrong with this then? That's kind of messed. Okay, so we clearly don't need that. At least I was able to figure it out. Oh my gosh. Beautiful. Okay. Let's word search. Do I remember how to do this? Oh, this is just it for search. Yeah. Okay, so. Oh, wait, no. It's like this, or false. It's IJ, board visited. Word index. Yeah, this is all shot right here. Visited string word and index. Okay. Otherwise, we gotta do this. Oh my gosh. Wait, I'm so dumb. I'm gonna just retype this all. Beautiful. That took way too long. Okay. I'm not gonna try this. So what have we not done? We haven't done this, 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 or this, or this. Okay, time to do graphs. Okay, now I can start like explaining stuff because I know what's going on, at least. Okay, so to count the number of islands, we just gotta iterate everything. Iterate the grid. And then if grid, if the current position equals 1, then we can delete the island using DFS. And then count plus plus. And then we will something like that. And then we just return the counter. Yeah, public void DFS. Or no, delete island. Row and call char grid. Was equals 0, return. Otherwise, we're going to delete that portion of the island and then call this. Oops. And then recursively call delete islands and perform DFS. Yeah, I think that's it. Cool. Okay. All right, I think I'm gonna finish graphs and then call it a day. Dang, I still haven't gotten these or these. We'll continue next time around. 0, 4. So here we have to iterate again through the grid. And if current position in the grid equals 1, we're going to reset max to the max between itself and count island, ij grid, or return max. Public void oh no, int count island. So this is going to be the same as delete islands, but we're going to return an iteration of all of the area basically. So if row is less than 0 and call is less than 0, or row is greater than or equal to dot length, or call is greater than or equal to grid row dot length, or grid row call equals 0, we're going to return 0. Otherwise, we're going to return count island, row plus 1, call, oh wait, no, we're going to return 1 plus this. Row plus 1, call grid, plus row minus 1, call grid, plus row call plus 1 grid, plus row call minus 1 grid. That should be it. Oh, wait. Forgot. We need to make it 0. We need to delete the island too. Cool. Okay. Oh, yeah, I'm gonna need to write down backtracking. I don't really know the time complexities of this stuff. Time complexity of graph problems. Yep. Oh man. So we have to make a hash map. Okay. And a queue, right? Put while the queue has something in it. that it? I might have just botched this. Yeah. Pull. What am I doing wrong? I think I need to restart this. Oh, I know what was wrong. I think that might be it. There we go. Okay. Oh, I don't even know if I remember this. Grid row call, prove. What? There we go. Oh my gosh. There we go. Cool. Sweet, we have like 20 more. I probably won't end up doing word ladder. Oh my gosh. Okay. Oranges. Yeah, okay. I think I'm gonna call it a day. It's been a little too long. Okay, cool. We will pick up next time around. Let's do a little recap. So today got a good overview of what we need to work on, at least for now. I mean, we covered how many problems? We covered 69 plus 21, so 90 problems that I already knew, obviously, but we got all these issues that we need to cover, which will take a lot of time anyways, and then yeah, and then we're preparing ourselves pretty well for what we need to know. And I would say I'm pretty happy with how few I didn't know. I mean, I think backtracking obviously was a struggle. I was actually surprised I got as many as I did for the priority queue questions, except for the task scheduler, obviously. Graphs. I mean, graphs are pretty straightforward. So yeah, we still have to go over intervals. There are a few greedy algorithms that I know and I've done, but I don't fully understand. Advanced graphs, these, for the most part, I'm aware of. I haven't done in a while, but I should be able to solve them in a timely manner. And if I don't, when I see the answer, if I see the answer, it'll come pretty quickly. So yeah, one-dimensional DP and two-dimensional DP, these I struggle with actually. So I would say like my biggest weaknesses are backtracking, 1DP, 2DP, just for like solving, not even time and space complexity. And then graphs, obviously, like I'm not fully versed in time space complexity. We still have some of the linked list stuff and trees, especially for space complexity, we're stuck with. But I mean, this foundation right here, I'm pretty comfortable with, but there's still a ton of work to do. So yeah, we'll see where we end up next time around, but hopefully we don't run into any of these situations again where we're missing days, because this was quite heartbreaking. But yeah, first stream done. That's a wrap.